Welcome back to another deep dive. Today we are going to do something a little uncomfortable. We are going to walk into a room that we all know very well, a room we've lived in our entire lives, actually, and we're going to stand in the middle of it and point at the pink elephant.
It is a very large, very pink elephant. And what's fascinating is that culturally, scientifically, and, historically, we have all collectively agreed to treat this elephant like it's just a decorative ottoman. We put our feet on it, we admire it, but we don't ask why it's there.
We are talking, of course, about the moon. But not just the moon, we are talking about the entire architecture of the solar system.
Wow.
I was thinking about this on the way in. When you look at a model of the solar system, like in a third-grade classroom or a museum, it's this perfect static mobile. Mercury is here, Venus is there, Earth is here. They move in these polite little ellipses. It feels permanent.
It feels like a museum display. That's the static fixture model. We treat the planets like they're bolted to the floor. We assume that where they are now is where they have always been. And more importantly, we assume that the current arrangement is the default setting. Like, this is just how solar systems look.
But the source material we have today, which I have to say is one of the most dense and mind-bending stacks of research notes, thought experiments, and systems archaeology papers I have ever read.
Yeah.
It completely flips that table over. It basically asks, what if we stop looking at the solar system as a museum and start looking at it as a billiards table?
A billiards table where the game is still being played, or perhaps more accurately, where we walked in 5 minutes after the break, the balls are scattered everywhere, and we are trying to figure out who took the shot and, how hard they hit the cue ball.
I love that image. We are detectives looking at the aftermath. And the biggest clue in the aftermath is the moon. Because when you actually look at the stats, the moon makes no sense.
It really doesn't.
Yeah.
In the context of the inner solar system, the moon is a freak anomaly. It's huge.
It is colossal compared to the Earth. If you look at Mars, its moons, Phobos and Deimos, are basically captured potatoes. They are tiny asteroids. Jupiter and Saturn have massive moons, sure, but Jupiter and Saturn are gas giants. They are gravity wells.
Right.
Earth is this relatively small rock, and yet it's lugging around a satellite that is a quarter of its own diameter.
It's like a chihuahua walking a Great Dane.
Exactly. And because it's so big, it's decisive. It controls our tides, it stabilizes our axial tilt, it dictates the length of our day. The source material calls it the pink elephant because it is a massive dynamical boundary condition. It's not just a pretty light in the sky, it's a dominant gravitational partner. And yet, we treat it like an accessory.
Dynamical boundary condition. That is such a heavy phrase. It sounds like something that stops you from doing whatever you want.
That's exactly what it is. It's a constraint. And the mission for this deep dive is to look at those constraints. Now, I want to be clear before we dive in. We aren't here to debunk the giant impact theory or claim aliens built pyramids.
Right. No tinfoil hats today. No. The goal is to explore what the source calls a non-centric framework. We want to build a way of thinking, a toolkit, that allows us to reconstruct the history of the solar system without assuming we know the answer before we start. We want to stress test the history.
So it's about creating a framework where the Earth-Moon system is an output of history, not an assumption. We're going to talk about some incredible concepts today. Harmonic archaeology, which sounds like a prog rock album, but it's actually about thermodynamics and planetary memory, which is this haunting idea that planets remember violence.
They remember it like the ring of a bell.
I can't wait to get into that. But let's start at the beginning. Or rather, let's start by destroying the map. This is section 1, decentering the solar system. The source material opens with this really provocative idea, it says. Imagine walking into a room and pinning labels to the walls. This is North. This is Earth. This is the way it has always been.
And the argument is that as soon as you pin those labels up, you stop thinking. You stop asking questions. You accept the map as the territory. But in a system as old and as violent as ours, the labels are often lies, or at least they're temporary conveniences. The first move of this thought experiment is to rip those labels down.
Let's start with the label North. I feel like I know what North is. It's up. It's where the compass points. It's where Santa lives. But the source says, not so fast.
This is a classic example of how we blur distinct physical concepts because it's convenient for us humans living in a quiet epoch. In a stable world, North seems like one single arrow. But physically, there are at least 4 different definitions of North, and in a young, chaotic system, they don't necessarily line up.
4 Norths.
Yeah.
Okay, let's unpack this. Walk me through them.
Sure. First, you have spin north. That's angular momentum. If you skin a top on a table, the axis it spins around defines north by the right-hand rule. That's pure physics. It's the vector of the spin.
Okay, that's the mechanical spin. Got it.
Then you have geographic north. That's just a convention we draw on the surface. We put a pin in the map and say, this is the pole. It's a coordinate system.
Right. That's for maps and navigation. Simple enough.
Third is magnetic north. That's defined by the orientation of the magnetic field generated by the dynamo in the core. And as we know, that wanders, it drifts, it can even flip.
And we'll definitely come back to the flipping later because that's a huge part of the memory concept.
And the fourth, which is one people don't often think about, is inertia or mass north. This is the axis defined by the planet's density distribution.
Wait, explain that one. Mass north. What does that mean?
Imagine a planet isn't a perfect sphere. Imagine it has a giant lump of heavy iron on one side or a massive impact crater on the other. The planet wants to spin in a way that balances that mass. Its axis of preference, the way it wants to spin based on its weight distribution, might be different from the way it is currently spinning.
So, if I understand this correctly, in a violent young solar system, a fluid solar system, as the notes call it, these arrows aren't all pointing the same way.
Exactly. Imagine a protoplanet that gets hit by a massive impactor. Its spin axis might tilt over. We see that with Uranus, which is basically rolling on its side. Its magnetic axis might scramble because the core fluids are sloshing around like a washing machine. Its mass axis might shift because you just blew a crater the size of a continent into the crust.
So you could be standing on a planet where the compass points, say, left, the stars are spinning forward, and the ground feels like it wants to wobble to the right.
Precisely. The norths decouple. If you are trying to reconstruct history, you can't just say north is north. You have to ask, which north? And how did they drift apart? It forces you to look at the planet as a dynamic, wobbling top, not a static globe on a teacher's desk.
This leads us to the idea of the mixing epoch. This really blew my mind when I was reading the source, the idea that Earth might not have always been here.
This is the danger of the museum view again. We see Earth at 1 AU1 astronomical unit from the sun. We assume it formed here, cooled here, and stayed here. But in a billiards model, planets migrate. Gravity is a game of contact.
So Earth could have been where Venus is. Or Venus where Earth is.
It's physically plausible. The notes discuss the possibility of a mixing epoch where the inner planets were shuffling roles.
Hold on. You're saying Earth might have been in Venus's orbit? That sounds like science fiction. I mean, we have rocks that are billions of years old. Wouldn't they show signs of being cooked by the sun if we were that close?
Well, close is relative in the early solar system, but yes, the conditions would be different. But remember, we are talking about the very early days, the chaotic formation period. The orbits weren't nice and circular yet. They were eccentric. They were crossing. The source even speculates, what if the moon wasn't formed from Earth at all? What if the moon was originally orbiting Mars? Or what if it was just a piece of free debris, a rogue planetoid floating around until Earth grabbed it?
That is a wild thought. The moon as a free agent.
Or a stolen artifact.
A stolen artifact. I love that. So much more dramatic.
But the key insight here is that the present is just one frozen frame in a film. If you pause a movie during a car chase, the cars might look parked, but they aren't. We are looking at a snapshot of a dynamic process and treating it as the default setting. If we want to understand the moon, we have to stop assuming it's our moon by birthright.
And if we stop treating it as the default, we have to look at the evidence that's actually there. Which brings us to the pink elephant itself, the moon and its weird neighbor, Mercury. This is section 2. The moon, Mercury, and the missing materials.
This is one of the most compelling compositional mysteries in the solar system. It's a puzzle that has bothered planetary scientists for decades. If you look at the moon and Mercury as a pair, they're opposites.
How so? Walk me through the comparison.
Well, look at Mercury first. It's the innermost planet. It's incredibly dense. It has a massive iron core that takes up a huge percentage of its volume. Something like 85% of the planet's radius is core. It looks like a planet that had its outer shell stripped off. It's core heavy.
Okay, so Mercury is like a peach pit without the fruit.
Yeah.
Just the hard, metallic center.
That's a great analogy. Now look at the moon. It's huge, but it's surprisingly light for its size. Its density is much lower than Earth's. It's made almost entirely of silicate rock mantle material. It has a tiny, almost negligible iron core.
So the moon is all fruit, no pit.
Exactly. All mantle, no core.
I see where this is going. It's a bookkeeping error.
It's a compositional tension. The source asks a very simple, very uncomfortable question. Where did the rock go from Mercury, and where did the metal stay from the moon?
So the speculation, and again, we're just exploring the framework here, not saying this is what happened. Speculation is, could the moon's silicates and Mercury's coreness be results of the same family of events?
Did a violent shuffling of the inner solar system strip the mantle off one body and deposit it as a satellite around another? Or did they both form from a debris disk that had already been sorted by some massive collision? It implies that the materials in the inner solar system were, let's say, redistributed.
That implies a game of celestial hot potato with billions of tons of rock. But here's the thing that always confuses me about capture theories, or even the really complex impact theories. You can't just grab a moon, right? Gravity doesn't work like a lasso.
No, it doesn't, and that's the central problem.
If something comes flying past Earth, gravity might bend its path, sure. But if it comes in fast, it leaves fast. It slingshots. It doesn't stick.
You've hit on the fundamental problem of orbital mechanics. To bind something, to capture it into an orbit, you must remove energy.
You need a break.
You need a break, you need friction, you need dissipation.
And space is a vacuum. There's no air friction. So if a giant rock flies by Earth, what on Earth slows it down?
This is where the source introduces a fascinating concept called climate regimes. They argue that the state of the planet itself determines whether it can catch a moon. They define 3 regimes.
Okay, let's go through.
Regime A is greenhouse locked. Think Venus. It's hot, high pressure, surface water is unstable, or exists only as steam. The atmosphere is hard and angry, it's not very squishy.
Right. Not much cushioning there.
Then you have Regime C, the isolated deep space regime. Think Europa or Enceladus or maybe a snowball Earth. The surface is frozen solid. It might have liquid underneath, but the shell is rigid. It acts like a hard billiard ball. It preserves things, but it bounces.
Okay, so you have hot and angry and cold and hard. What's regime B?
Regime B is the sweet spot, the phase change ocean. This means you have liquid water on the surface that is actively evaporating, freezing, melting, and flowing. Why does that matter? Because water is heavy and water moves.
Sloshing.
Sloshing is exactly the scientific mechanism we need here. Imagine a massive object like the moon passes close to Earth. Its gravity pulls on Earth. If Earth is a solid rock, it distorts a little bit, a body tide. But if Earth is covered in deep liquid oceans,
The oceans bulge massively.
they bulge massive amounts, and as the moon moves, that bulge has to travel across the planet. It drags across the seabed, it crashes against continents. That drag creates friction, it generates heat.
Wait, so it converts the orbital energy of the moon into heat in Earth's oceans.
Exactly. It bleeds energy out of the system. It acts as a massive planetary brake. The source calls regime B a dissipation engine.
That is incredible. So the argument is that because Earth had these sloshing oceans, because we were in this specific climate window, we were able to slow the moon down enough to keep it.
It's a beautiful connection between climate and orbital mechanics. If Earth had been frozen solid or boiled dry, the moon might have just waved goodbye and kept flying. Our oceans acted as the catcher's mitt.
That makes the oceans feel so much more functional. They aren't just where the fish live. They are the brakes for our satellite. But catcher's mitts get worn out, and if planets are getting hit and swapping moons, they must have scars. Which leads us to Section 3, planetary memory.
Planetary memory is such a poetic phrase, but the source means it quite literally. Planets are not just static rocks, they are stratified engines. They have layers, crust, mantle, core, and when you hit them, they remember it.
The source uses a really vivid comparison. A planet remembers not like a mind, but like the ring of a bell.
Yes, that is the physics of shock. When you strike a bell, the sound doesn't just happen at the point of impact. The whole structure vibrates. The energy travels through the metal, bounces off the boundaries, and sets up a resonance. Planets do the same thing.
And we have seen this happen in real time, right? The source points to Shoemaker-Levy 9.
1994. That was a pivotal moment for planetary science.
I remember seeing the pictures on the news, the comet that hit Jupiter. It was this string of fragments.
Before that event, impacts were often thought of abstractly. A rock hits a surface, makes a crater. Simple. But Shoemaker-Levy 9 didn't just hit the surface. It was a train of fragments, like a string of pearls, that hammered Jupiter, one after another, like a machine gun.
And the marks it left, they were huge.
Those bruises were bigger than Earth, giant black welts in the cloud tops. But more importantly, the impact excited the entire atmosphere. It sent waves traveling around the planet. It proved that the target is a fluid medium, the energy deposited into the deep layers. It rang the bell of Jupiter.
So that's immediate memory, the bruise. What about long-term memory? The source points to Mars and Valles Marineris. Now, I always thought Valles Marineris was just a big canyon. Like the Grand Canyon, but, on steroids.
It is often described that way in introductory texts. Oh, maybe water flowed here once. But the scale is incomparable. It stretches across a huge swath of the planet. The source describes it not as a crater or a canyon caused by erosion, but as a structural confession.
Structural confession.
Yeah.
That gives me chills. It sounds like the planet is admitting something.
It admits that it broke. The leading theory, which the source supports, is that Valles Marineris is a tectonic crack, a stretch mark. Mars has this massive volcanic region called Tharsis, huge volcanoes like Olympus Mons. The weight of that lava piled up on one side of the planet
Made the planet top-heavy, like our mass north idea.
basically. The stress was so immense that the crust just tore, it split open. Valles Marineris is the scar of that stress. It records a moment where the planet's internal structure couldn't handle the load.
So if Mars has a giant tear and Mercury has a missing mantle, what about Earth? We have plate tectonics. Doesn't that erase everything? I thought the whole point of subduction was that it melts the crust and recycles it.
That's the conventional wisdom. Tectonics recycles the crust, it hides the crimes. But the source flips that logic. It suggests that tectonics is the memory.
Explain that. How can the recycling process be the memory?
Think about a scar on your skin. If you get a deep cut, the body repairs it. But the new tissue is different. It's tougher, or it has a different grain. It's a pathway. The source suggests that plate boundaries, subduction zones, the deep trenches might be the long-term repair mechanisms of ancient trauma.
So a trench isn't just where plates happen to meet today, it's there for a reason.
It might be a pathway of least resistance that was established billions of years ago.
By what?
By a massive event. Imagine Earth gets cracked by a huge impact or twisted by a capture event like the moon arrival. The planet has to deal with that stress. Oceans flow to the lowest point, right?
Right.
Well, the crust flows to the point of weakness. Subduction trenches are the deepest pathways. The source argues that the deepest trenches might be part of the planet's shock absorption system. The planet routed the stress into a cycle of subduction.
That reframes the entire map of the ocean floor for me. It's not just geology, it's scar tissue. It's the planet trying to hold itself together.
Exactly. And there's one more layer to this memory, perhaps the most subtle and speculative one: magnetic memory.
This part was fascinating. Geomagnetic reversals. We know Earth's magnetic field flips north and south every few 100,000 years or so.
Right, the compass flips.
Usually we are told this is just randomness. The fluid in the outer core is turbulent, it gets unstable, and floop, it flips.
That's the standard dynamo theory. But the source frames them as relaxation modes.
Relaxation modes, like taking a deep breath.
Use a different metaphor. Think of a telephone cord. You know, the old coiled one.
Oh, I miss those. They were so satisfying to play with.
If you twist it and twist it, eventually it gets so tight that it snaps into a knot to relieve the tension. It changes its geometry to handle the stress.
Okay, I can visualize that. It bunches up.
The source suggests that a magnetic reversal might be the planet snapping, like that cord. If the Earth system is torqued or twisted by an external force like a massive gravitational encounter with another planet, the electromagnetic state might flip to release that accumulated distortion.
So a magnetic reversal might be the planet cracking its back after a long period of stress.
Precisely. It implies that the frequency of these reversals, how often they happen, might tell us about the stress the system was under at that time. If the flips are happening constantly, maybe the system is being bullied.
Being bullied by whom? That's the question. We've looked at the planet itself, the scar tissue, the magnetic flips. Now let's look at the neighbors. Section 4, neighborhood clues.
Because we aren't alone in this room.
No, and the biggest person in the room is Jupiter. We cannot talk about solar system architecture without talking about Jupiter.
The source calls Jupiter a sculptor or a bouncer.
A bouncer. I like that. The source mentions Kirkwood gaps. I'd never heard of these before. What are they?
If you look at the asteroid belt between Mars and Jupiter, you might imagine a solid field of rocks, like in Star Wars.
Never tell me the odds.
Right, but it's not like that at all. If you map the asteroids, there are empty lanes, distinct gaps where there are basically zero asteroids. These are the Kirkwood gaps.
Why are they empty?
Resonance. These gaps correspond to specific orbital ratios with Jupiter. For example, there's a gap at the distance where an asteroid would orbit exactly 3 times for every 1 time Jupiter orbits. This is a 3.1 resonance.
And why does that clear the gap? It seems counterintuitive.
Think of pushing a child on a swing. If you push at the exact right moment every single time they come back, what happens?
They go higher? And higher, and eventually they get scared and jump off.
Or they fly off the swing. Jupiter is pushing the swing. Every time the asteroid passes Jupiter, it gets a gravitational pick. Because they are in resonance, the kick happens at the same point in the orbit, over and over. This pumps up the asteroid's orbit until it becomes unstable and gets ejected.
So Jupiter's actively clearing these lanes. It injects chaos inward.
Injects chaos inward, that's the key phrase. Jupiter throws rocks. It takes asteroids from the belt and slingshots them into the inner solar system toward Mars, toward Earth.
So the asteroid belt isn't just a junkyard, it's an ammunition depot.
And Jupiter's the one firing the cannon, and we see the evidence of this bombardment in things like the torrid meteor streams.
The torrids. These are the shooting stars we see in October and November, right?
Yes. The source highlights them as evidence of debris streams. The torrids are associated with comet ink. They are a massive river of rubble that Earth intersects on a schedule.
Why is that important for this archaeology? What does that tell us?
Because it proves that memory survives in space. This isn't just random dust scattered evenly. It's a coherent family of fragments that has stayed together for thousands of years. It shows that when something breaks, like a giant comet fragmentation event, the pieces travel together, they form a family.
It's forensic evidence. If you find a stream of blood drops, you know the victim was moving in that direction. The torrids, the blood drops of a dying comet.
A bit grim, but accurate. It validates the idea that we can look at groups of objects and trace them back to a single violent event.
And then there are the visitors from outside, the external intruders.
Objects like a Oumuamua or Tua Borisov.
The cigar-shaped thing that flew past a few years ago, that was so weird.
Exactly. These are interstellar objects. They come in on hyperbolic trajectories.
Hyperbolic means what in this context? Just really fast.
It means they're moving too fast to be captured by the sun's gravity. They fall in, they whip around the sun, and they leave forever. They are just passing through.
They are tourists.
They are boundary conditions. They prove the system is open. We are not in a sealed bubble. Things can come in from the outside, disrupt the billiards table, and leave. It adds another layer of unpredictability.
Okay, so let's pause and look at the picture we've painted. We have a fluid system, we have planets acting as brakes, we have scars, we have Jupiter throwing rocks. This feels like total chaos.
It does. It feels like a mess.
But, and this is the pivot, the source material argues that there is a hidden order underneath it all, a structure that dictates where the planets end up. This is the aha moment of the episode. Section 5. Systems archaeology and harmonic resonance.
This is the deep science. This is where we get into the constraint stack. The source proposes a method for reconstructing the system using thermodynamics. It's a logic chain. A leads to B, which leads to C.
Okay, I want to really take our time here. This is the core argument. Let's break it down. A, B, C. What is A?
A is the star. In our case, the sun.
Yeah.
The star sets the energy field. It's like a giant heat lamp in the middle of a cold room. The closer you are, the hotter it is. That is the baseline constraint. Simple enough. The sun is the boss. What is B? B is the phase transitions. This is the harmonic ladder. As you move away from the star, the temperature drops. At specific distances, the temperature drops low enough for specific materials to change from gas to solid. We call these snow lines.
Like on a mountain, you go up high enough, rain turns to snow.
Exactly. But in space, it's not just water. There is a ladder of these transitions. The source identifies 3 specific rungs on this ladder based on the chemistry of the protoplanetary disk.
Okay, let's climb the ladder. What's the first rung?
The first rung is water. In a typical solar nebula, water freezes into ice at about 170 Kelvin.
170 Kelvin. That's cold.
That's about a negative 100 degrees Celsius, yeah.
Oh.
Very cold. But in space, that's the point where water vapor turns into ice grains.
And where is that in our solar system?
If you do the math normalizing for the sun's luminosity, that temperature boundary sits at roughly 2.7 AU between Mars and Jupiter.
Okay, hold that thought. 2.7 AU. What's the second rung on the ladder?
The second rung is ammonia and related mixtures. That phase transition happens much colder, around 80 Kelvin.
And the third?
Carbon dioxide and carbon chemistry. That's even colder, around 70 to 90 Kelvin.
So we have these invisible lines in space. 170K, 80K, 70K, that's B. Now what is C?
C is the architecture, the planets themselves. The argument is that planets don't just form anywhere. They tend to form or settle near these boundaries.
Why? Why does a snow line make a planet? What's the mechanism?
Because snow lines are traps.
Yeah.
Imagine you are a dust grain floating in the gas. When you hit the snow line, suddenly all the water vapor around you turns to ice. It freezes onto you. You get sticky, you get heavy. The density of solid material spikes at that line.
It's a traffic jam.
It's a massive traffic jam. Material piles up. And where material piles up, gravity takes over. Pebbles become boulders, boulders become planetesimals, and planetesimals become planets.
So the harmonic archaeology test is, do our planets sit on these rungs? Let's check the math. You said the water rung is around 170 Kelvin. Where is Jupiter?
Jupiter sits at 5.2 AU. If you calculate the effective temperature out there in the early disk, it's about 122 Kelvin. Now, you might say, that's not 170. But in terms of disk structure, it is right in the water ice enriched annulus. It's just past the snow line where the huge abundance of ice became available.
So Jupiter formed because there was suddenly enough ice to build a giant core.
Exactly. It parked at the buffet at all-you-can-eat ice.
Okay. What about Saturn? Where does it sit?
Saturn is at 9.54 AU, the temperature there, about 90 Kelvin.
And the ammonia CO2 run was?
Around 80 to 90 Kelvin. Saturn is sitting almost exactly on the nitrogen-carbon rung.
Wow. Okay, that's a direct hit. And Uranus?
Uranus is at 19.2 AU. The temperature there drops to about 64 Kelvin. That is right in the neighborhood of the carbon dioxide and carbon monoxide transition.
This is the inverse archaeology mentioned in the text. You look at where the planets are, calculate the temperature, and you realize, wait a minute, they're parked exactly where the chemistry changes.
It suggests the planets aren't randomly thrown on the rug. They are spaced according to a thermodynamic ladder, the harmonic ladder. They settled in the zones where matter changed state.
That is incredibly satisfying. It makes the solar system feel designed, not by a person, but by physics.
It's self-organizing. It means that if you know the star, A, you can predict the snow lines, B, and if you know the snow lines, you can predict where the planet C should be.
But there's a twist, isn't there? Because big planets don't just sit there. They change the rules. This leads to section 6, catalytic closure.
Right. This part gets a little heady, but it's crucial. It mentions Kaufman influence.
Stuart Kaufman, the theoretical biologist. What's he got to do with planets?
He talks about complex systems, life, economies, ecosystems. He argues that causation isn't just a straight line, it's a loop. A creates B, B creates C, but then C helps maintain A.
Catalytic closure. So how does that apply to a planet? A planet is just a rock. How does it maintain anything?
We just said ABC, star may snowline planet, but the source argues it's actually ABCB.
B prime. What's B prime?
Once the planet forms, C, it changes the disk. Think about Jupiter. It's massive. As it grows, it clears a gap in the disk. It acts like a dam in a river.
It changes the flow of gas and dust.
It changes the pressure. It changes the opacity, how much light gets through. By clearing the gap, the planet effectively locks the temperature profile in place. It stabilizes the snow line that created it.
So the planet acts as a shepherd for its own snow line.
Exactly. It preserves the boundary condition. It's a feedback loop. The trap creates the planet, and the planet maintains the trap. This is why the structure is so stable. It's not just a rock floating in space. It's a self-sustaining engine of thermodynamics and gravity.
That is wild. It means the planet is an active participant in its own history. But this is all theory. The source material is very insistent that this needs to be a runnable test. We can't just tell nice stories. We need to prove it.
Yes. Science requires a deliverable. You have to be able to test it.
So how do we test this?
Yeah.
We can't build a new solar system.
No, but we have thousands of other solar systems to look at. The exoplanet test.
The NASA Exoplanet Archive.
Right. But here's the problem. If you look at the raw data of exoplanets, it looks like a zoo. Hot Jupiters, super-Earths, mini-Neptunes, they're all over the place. Some are close to their star, some are far. It looks random.
So how do we find the order in that chaos?
You have to normalize. You can't just compare kilometers or miles. A planet at 1 AU around a dim red dwarf is frozen solid. A planet at 1 AU around a blue giant is vaporized.
Distance doesn't matter. Temperature matters.
Exactly. We need to put on thermal goggles. We need to map every exoplanet not by how far is it, but by how much energy does it get. We normalize by the star's luminosity.
We create a harmonic map.
Yes, and the prediction from the source is this. If you take all these thousands of different star systems and scale them based on temperature, the chaos should disappear. The planets should cluster.
We should see peaks in the data at the water line, the ammonia line, the CO2 line.
Exactly. We should see the same rungs of the ladder appearing again and again across the galaxy. And the source adds a specific detail. The peaks should sharpen with planet mass.
Why is that?
Because bigger planets create stronger traps. A Jupiter-sized planet will lock onto that snow line much tighter than a tiny rock. It digs a deeper hole, so the massive planets should be the most predictable.
It turns the philosophy into a runnable code. I love that. If the peaks are there, the theory holds. If the distribution is flat, the theory is wrong.
It's falsifiable. That's good science.
Now, before we wrap up, there is one more clue in the source material that is just weird. It's almost like an X-Files episode. Section 7, the latitude clue.
Ah, yes. The 42 degrees N motif.
The source mentions a working list of 17 major impact structures, craters, anomalies, that seem to cluster around 42 degrees north latitude. Now, immediately, my skepticism alarm goes off. That sounds like numerology. That sounds like finding faces in clouds.
It does, and the source is very careful to call this a toy clue or a hypothesis starter. They are not claiming 42 is a magic number or the meaning of life.
Though Douglas Adams would be pleased.
He would, but they are asking a valid statistical question. Do impacts show a preference?
But wait, the continents move. 42 degrees north today wasn't 42 degrees north 100 million years ago. North America has drifted.
Precisely. That's the pivot. The real test isn't modern latitude, it's paleo latitude. Where was that land when the rock actually hit?
So if we correct for continental drift, if we rewind the tape and we still see a clustering, what would that mean?
It implies geometry. If impacts are coming in randomly from everywhere, like rain, the map should be speckled evenly. If they are clustering in a band, it tells us something about the incoming direction of the debris.
It means they were aimed.
Or focused. Maybe the Earth had a temporary ring of debris like Saturn's rings that decayed and rained down along a specific latitude, or maybe it connects back to our north discussion. Maybe the Earth was tilted differently then.
Or shielding. Could something have blocked impacts from other directions?
Or shielding. Maybe the Moon or Jupiter was blocking certain angles, leaving only a specific window open for impacts.
It's another way of saying, look for the pattern. Don't assume it's random noise.
That is the theme of this entire deep dive. Noise often contains the signal of a history we haven't learned to read yet.
So let's bring it all home. We've covered a lot of ground today. From the pink elephant moon to the harmonic ladder. Let's try to summarize this framework in the outro.
The core takeaway is the constraint stack. If you want to understand the solar system, don't just look at the positions of the planets. Look at the constraints.
Step 1. The star sets the energy.
Step 2. The energy creates phase harmonics, the snow lines.
Step 3. The harmonics create the architecture. The planets form at the traps.
And step 4. The planets look back and stabilize the harmonics catalytic closure.
And within that system, we have the pink elephant. The moon isn't just a decoration. It's a massive boundary condition. It demands an explanation, and that explanation involves the dissipation engine.
The oceans that catch the ball, the oceans that act as the brake.
And we have memory. The idea that planets wear their history. Valles Marineris is a tear, the trenches are scar tissue, and the magnetic field is a stress ball snapping back.
It shifts our philosophy. We are not replacing the giant impact theory. We aren't saying everything you learned in school is wrong. We are saying remove the static fixtures. Stop treating the solar system like a finished painting.
Treat the present as evidence, not the origin.
The present is the crime scene, not the biography.
That is such a powerful shift. We must view the solar system as a dynamical ecology. It's a living, breathing system where the moon is the output of a chaotic, beautiful history that we are just starting to read.
The source material leaves us with a final thought that I think is perfect to end on. May the next questions you ask be sharper than the answers you inherit.
That is the essence of science. Don't just accept the answers given to you by the previous generation. Use them to sharpen your own questions. Look at the pink elephant. Ask why it's there. And on that note, we'll leave you to look up at the moon tonight and wonder, how did you really get here? And what else are you remembering? Thanks for listening to The Deep Dive.
Keep looking up.